Welcome to a new lesson. In this video we are going to look closely at how vapor compression refrigeration system behaves in real world conditions, beyond the life cycles we've seen before. We'll examine where and why deviations occur and what this means for HVAC design. This video is structured around three major concepts. First, we'll explore how real vapor compression cycles deviate from the ideal due to practical limitations like frictions, pressure drops, and imperfect heat transfer. Then we'll use a pH diagram and TS diagram to visualize how these deviations shift the cycle's shape, requiring more compressor work and reducing cooling effect. Finally, we'll examine the practical consequence for HVAC design, how acknowledging these losses supports smart component choices, accurate modeling, and more efficient systems overall. By the end of the video, you will be able to identify the main difference between the ideal and real vapor compression cycles and explain how factors like pressure drops, non-isentropic compression, and heat exchanger losses affect real-world system performance. But let's begin with a question. If the vapor compression cycle is well understood and designed using ideal assumptions, why don't real systems follow that behavior exactly? What could be happening that make the difference in the real world? In this video, we'll encounter the physical and technical reasons behind these deviations. In a real compressor, the compression processes deviate from the isentropic assumption to mechanical losses, friction, and internal heat transfer. These irreversibilities increase entropy and require more input work, which leads to a lower actual efficiency than the ideal model predicts. Additionally, heat gain from the surrounding can raise the temperature and the suction gas, further increasing the compression load. In the condenser and evaporator, the refrigerant doesn't undergo ideal heat exchange. The pressure drops occur due to flow resistance and surface imperfections, with altered enthalpy values at inlet and outlets. This reduces the effective temperature difference driving heat transfer, lowers heat exchange effectiveness, and increases system energy consumption. The pressure drops also means the refrigerant may condense or evaporate over a wider range of conditions that assume in ideal models. Superheating and subcooling are practical necessities, but they introduce additional deviations. In real systems, superheating at the evaporator outlet ensures vapor enters the compressor, preventing liquid slugging. Subcooling at the condenser outlet avoids a flash gas formation. However, both can extend beyond the minimum needed, introducing thermal mismatches and require more energy to maintain desired performance levels. These practices also shift enthalpy states and affect refrigerating capacity and system control strategies. Let's now explore the real vapor compression cycle using two important tools, the TS diagram and the pH diagram. On the TS diagram, we can see that compression in a real cycle does not follow a vertical line. The entropy increases during compression due to friction and internal losses. Likewise, the expansion process does not happen instantly at the heat transfer during condensation or evaporation. And evaporation, they occur over a broader temperature range. These areas represent real energy exchanges and losses that deviate from ideal assumptions. On the pH diagram, the real cycle path is visible disorder compared to the ideal. Compression starts from a superheated state and ends at a higher enthalpy due to inefficiencies. Expansion begins from a subcooled liquid, but pressure losses in the expansion valve and the evaporator further reduce the refrigeration effect. Together, these diagrams help us quantify how much extra work is required and how the subcooling effect is diminished. This deviation results in increased compressor energy consumption and a lower coefficient of performance. Understanding these shifts help us design better systems and anticipate their real-world efficiencies. Because of known idealities, engineers must select components such as compressor, expansion devices, and heat exchangers that can operate reliably under fluctuating loads, pressure drops, and real thermal gradients. This means accounting for part load conditions, ambient temperature variations, and refrigerant properties that deviate from textbook behavior. Accurate modeling of the real cycle is essential for predicting performance, selecting control strategies, and estimating seasonal energy efficiency ratios. Tools like TS and pH diagrams, combined with empirical corrections factors and manufacturer data, improve the reliability of simulation results and design outcomes. Understanding the impact of real cycle losses, such as pressure drops, superheat merging, or compression inefficiency, help us engineers make informed decisions that improve system efficiency. This includes optimizing refrigerant selection, sizing heat exchangers, and applying advanced control strategies to reduce energy use without compromising performance. Let's recap. Real refrigeration cycle deviates from the ideal because irreversibilities like friction, heat losses, and non-instantaneous phase changes. These factors reduce efficiency and raise energy consumption, especially in compressors. Understanding real behavior is critical to designing HVAC systems that perform reliably and sustainably. You are on the right track. In the next videos, we looked at enhancements to the vapor compressor cycle, strategies to improve energy efficiency, and real case studies that show how system optimization works in practice. Let's continue.